you. Hello everybody. First I want to thank all of my co-authors for their contribution to what I present here. The title is Spectrally High Resolution of Satellite Remote Sensing of Vegetation. So what is it about? Typically, commonly used vegetation classification are based on multispectral sensors like spot instrument or the Mahr, sometimes also on hyperspectral sensors. Where I came from, it's an institute where we make atmospheric measurements of trace spaces. We use very high resolve spectra, so typically 10 channels per nanometer, like Maki, GOM, or GOM2 instruments. And so the idea was the instruments we use also take information about the light which is reflected from the ground surface. We can use this information to actually increase, well, we have more information about the ground surface, and the question is if this can increase the classification to distinguish more groups of vegetation. So first, what I present here now, first we have to measure high-resolve reflection spectra. Then we did a classification of this, and we also want to start with the aggregation of satellite data. I apologize, but I cannot present it here because until now we are not in the stage for this. So we built up an instrument and took a lot of effort to get really high-quality data for vegetation measurements. So basically we have light sources illuminating the sample area. We can put leaves there, and then the light is collected by a telescope and measured by a spectrometer. And we have a reference plate for reference measurement. And the wavelength range is from 350 to 1050 nanometer at a resolution of 0.29 nanometer. The width has maximum, which means around 20 channels per nanometer. So this is now a random selection of samples we measured. We have the reflectivity and the logarithmic scale and the wavelength. And what you can see now here, first we have a very low reflectivity in the ultraviolet region because of anthocyanins here protecting the leaf from harmful radiation. And then this typical shape for plant spectra. Here this part is described by the curve being chlorophyll in the light harvesting complexes. Here's the main absorption of chlorophyll, and then we have this typically strong rise in the reflection from the red to the infrared region called the red edge. So this is the part where also the NDVI is calculated because it's very typical for plant spectra. What we are interested in is the exact shape of these three different waves and also in the red edge. And to compare these measurements a bit better, I will apply a high-pass filter, which removes the broadband part of this, and this is how it looks then. And what you can see is that actually these waves are very constant in position for all of the samples we measured. So they are within 1 nanometer, except for this part here describes the red edge. And you can see that this is the part where the plants differ most. So the amplitude is different, the position is different, and also the width. For the evaluation of satellite data, we want to use then this part more or less because the changes are strongest. So in total, we measured 95 samples, mostly from the greenhouse of the botanical garden and also from the surroundings, and we used them to do a classification vegetation, and I represent not all of the results, but the most interesting ones. First, we applied principal component analysis on all these spectra, and what you can see here, each dot represents one plant. So this is the first principal component, the value for the first plant, and then the second, and so on. And as I said, we had three different plants from the greenhouse and the surrounding here, surrounding in red. And what you can clearly see is something very astonishing, because we can really distinguish between, not distinguish, but you can really see that, for example, here the values from the surrounding have a different value than from the greenhouse. And this was actually not what we expected, because we wanted to see somehow genetic differences to the species and not just where they come from. And here this is also in the hyperspectral spectra. So we have both groups again in red and in black, and the variation within each group is here now plotted as Y arrow, and you can see that they really look different no matter what species they are. So the second thing or what most interesting results we found was from the botanical class. Here are shown now only samples from outside, and we have coniferous trees and deciduous trees, and well, you can see that actually there are differences, for example here, but the differences are very weak. I will show the same plot here. But you can see that in the red edge region there are differences, but in the rest there are not. And one example where you can't see any differences, this is an extreme example. We looked at plants from the desert and from the tropics, which are typically quite different. But you cannot see this in the spectrum, which is quite astonishing. So here now an overview of things we investigated. The first four are according to the botanical systematics. So we have the botanical class, which I showed you, the botanical order, botanical family, and the unranked order, which did not show any differences for the different groups. For the environment, this was the first part I showed. We have the type of photosynthesis, which means common and C3 plants. We did not have enough C4 plants to do the investigation. We also analyzed climate zone and continent, but this did not show anything. So the question is, why can't we see anything? Because other centers can see more. And well, there was the idea that we measured simply little leaves, and maybe we wanted to investigate what are actually the variation of leaves. There's two different leaves from the same tree. Are they different or are they the same? So we did another study. These are the results of this. So this is just the order of magnitude, how big the variations are. So this is the order of magnitude of the variation for the classification I showed. And then there are several different things which we analyzed. For example, if you measure the same plant on the same day, one leaf from the north side and one leaf from the south side, they differ about 9%, which is quite a lot compared to the classification. Or we measured, if you take just neighboring leaves, also from the same plant, they're around 6%. If you measure them from different trees, they're around 8%. And also the environment or the time, when you measure the same plant every 2 weeks, you can have variations there. So we also some summary. We measured 93 plants, very high resolution, and the biggest differences we found were from the surrounding and the greenhouse, from where they come from, but not for which species they are. And the outlook of the evaluation of satellite data, we want to fit the main vectors of the first principal components of the principal component analysis, and then define reference training areas, and finally to create global maps, or also to see how much groups you can actually distinguish. Thank you.
Thank you for your presentation, Tobias. Got time for a couple of questions.
I have a question. You mentioned that the measurement was done on the leaf level. Is it done in an integrating sphere, or is it done in a predefined angular setup? Is it done in laboratory, all of it?
It is a defined setup, so we measured from perpendicular, and the light sources were arranged to actually cover different angles. We also thought about actually measuring the angle dependencies, so from different viewing direction and also different light, but we did not do this until now.
So you detached the leaf, moved it to laboratory,
Yeah, right.
and you got such a big difference between the outdoor plants and the greenhouse plants of the same species on the leaf level.
No, they were not the same species, because actually they are in the greenhouse because they do not grow outside. There was only one species. It was a bamboo tree which we had from outside and inside, but it also has the same differences, and so from outside and inside. We're not sure what it is. It may be because in the greenhouse the plants are fertilized, and this can make a big differences. There was last year at the IGARSS conference, there was a lady showing something else for cornfields. She could distinguish organic fields from non-organic, because the organic are not allowed to be fertilized. Or it could also be because in the greenhouse we have absorbing glass, which takes out the ultraviolet light, and maybe the plants can adapt to this organic chemical.
Thank you very much.
I have one question about why do you just do the measurements of the spectra on the laboratory without the canopy structure? Because the canopy structure has large influence on the vegetation spectra, especially for the near-infrared band. So why don't you just measure the spectra out the door and with the canopy structure? And I think that might help you to classify the vegetation types.
Actually, measuring outside is also one thing we want to do. For example, from a tower or something, or from our institute, fields around there. But you can imagine that it's not that easy to perform these measurements. And you always have a lot of atmospheric distortions outside, because you need natural light source and not artificial. That's why we did it inside in the lab.
Hi, your results were, if you wanted to differentiate different species of plants from this remote sensing, your results seem to say it's pretty disappointing, it'd be very challenging. Do you think any additional data you could measure that would make it easier? You know, your spectrometer was, say, a limited range. If you had a wider spectral range, do you think it would be more optimistic? Or
I'm not sure.
Sorry.
Because
Thank you, Tobias, for your presentation.